So dear students, welcome to another lecture of digital control system. In this particular lecture, we will discuss about the inverse Z transform. Now, as far as Z transform is concerned, Z transform is used to uh, find out the uh, or do the frequency analysis of any discrete time system or discrete time sequence. So when we have to find out the solution of any Z transform, for example, if you have a sequence, let us say xn, for example, this is 1 and 0 and 2 and 1, for example, like this, right? Now, if you have to find out its Z transform, then its Z transform will be obtained by using the standard formula. Now, this is a finite sequence, and this is a causal sequence basically. Now, since no identification is given here that whether it is a causal or non-causal, so by default we have to consider a given sequence as causal until unless an arrow is given. For example, if you have a sequence like this, the same sequence for example, and if an arrow is given here at this point, so then this is a left sided finite sequence, right? This is a left sided finite sequence. This is a non causal sequence, right? And if xn is, let us say, same xn is given to 1 and an arrow is given here, then this is a right sided finite sequence, and this is a causal sequence. Now a causal sequence is the one, or causal signal is the one in which we have only uh, past and present data, right, information. However, a non-causal is the one in which we have a future information also, future data points also. Now, as you see here in this particular sequence, no arrow is given. So, what we have to consider this sequence, whether this sequence is a causal sequence or this is a non-causal sequence. So, as I have mentioned before also, that by default we will consider this as a causal sequence, and it is a right-sided sequence. So this one is the zeroth sequence, this is first sample, this is second, and this is third, right? So that means here n starts from 0 to 3, and we have xn z raised to the power minus n, right? So this is how we will take this one. Now there are certain notations of Z transform in different books. In some books you'll find xn, in some books you'll find xk, right? So this is one and same thing. N and k represent the same uh, point basically, or n and k signify the same point, that is the number of samples, number of samples. So don't get confused with the notation. Xn and xk are same. There is no difference. It is only the way of writing, right? In some books you'll find xk as a discrete time sequence. In some books you'll find xn as a discrete time sequence, right? So now the Z transform of this sequence will be xz, and it is x0 z raised to the power minus n minus z raised to the power 0, sorry, and plus x1 z raised to the power minus 1 plus x2 z raised to the power minus 2 plus x3 z raised to the power minus 3. Now this is the z transform of this one, and here we will put the values here. So x0 is 1, x0 is 1, right? And x1 is 0. So z raised to the power 0 is also 1, plus x1 is 0 into z raised to the power minus 1, plus x2 is 2 into z raised to the power minus 2, plus x3 is again 1 into z raised to the power minus 3. So it is 1 plus 2z inverse square plus z inverse cube. So this is the xz of the given sequence, right? Now if you have to find out its uh, solution, okay, if we have to find out the solution of given z transform, right, is the by taking the inverse z transform of xz, and this will give you xn or xk, right? So that means if you apply the inverse z transform of the z inverse z transform on the given sequence, you will get the solution of that particular uh, sequence, that particular z transform. So z transform is used to bring a system or a discrete time sequence or a discrete time system or a signal from time domain to frequency domain, right? And inverse Z transform is used to bring the same system, same sequence from frequency domain to time domain, where t is taken as kt, that is, it is the sampled time, right? It is the sample time. So as you can see here, inverse Z transform is used to convert the Z transform back to its original sequence, right? So original sequence means we are calculating or we are determining the solution of the given sequence, right? Then uh, so by applying inverse Z transform, we get xn from xz. So this is what the inverse Z transform does, right? Now there are certain methods to do the inverse or to apply the inverse Z transform to find out the solution of the given Z transform. And these methods are like, the first method is the long division method, which is also known as power series expansion method. And the second method is the partial fraction expansion or partial fraction method. And the third one is the residue method, which is also known as counter integral method. However, among these three methods, the most common methods or mostly used methods of applying the inverse Z transform to obtain the solution of a given Z transform are long division method and partial fraction method. So let us understand these methods. The long division methods. Now what is long division methods? Like every Z transform, not every Z transform in fact, sometimes the Z transform of any given sequence, so it is the Z transform of a given a sequence xn for example, so it is represented in terms of numerator and denominator. For example, we may have a xz transform like this: z square plus 2z plus 1 divided by z plus 1. So this could be the z transform of any given discrete time sequence, discrete time signal. This is possible. Now in this case, what we will do, we apply the long division. So we divide these two, right? So numerator is z square plus 2z plus 1. So we divide it like this. And then we get certain quotient here, right? Now this we will take, this quotient we will take and we will try to find out the uh, solution of this particular Z transform. Now, while applying long division method, we need to take care of certain things. One is whether the given sequence would be a causal sequence or a non-causal sequence. So for causal sequence, the xn would be existing for n is equal to or greater than 0. So this is a right-sided, right? Right-sided or a causal sequence, right? Or causal system. Similarly, for n less than 0, we have a non-causal sequence. Now, what does it mean? It means that we will understand this with an example, right? Now, for example, we have a sequence xn, which is a causal sequence 1, 0, and 2 and 1. The same, right? So, this is a causal sequence, right sided. So, this is a right sided causal, right? Now, if we take the z transform of this one, we will get xz is equal to 1 plus 2z minus 2 plus z in minus 3, z raised to the power minus 3. Similarly, if the same sequence is a non-causal sequence, so it is, let us say, 1 and 0 and 2 and 1, and it is a non-causal sequence, right? So this is the left-sided non-causal, right? So the z transform of this would be summation. So and n is from minus 3 to, let us say, 0, or let us say minus 1, right? Generally we do not take 0 here, so it would be minus 4, minus 3, minus 2, minus 1, like this. So n is from minus 4 to minus 1, because if it is 0, if we are taking limits from something to zeros, and then it would be a causal sequence, right? It would come under this one. So generally a non-causal sequence has the negative data points on time axis, that is the future values, future points basically. Okay, so it is x and z raised to the power minus n. So if we put the values here, we'll get x minus 4z 4 plus x minus 3 z3 plus x minus 2 z raised to the power 2 plus x 1 z raised to the power minus, or z raised to the power 1, or something like that. Okay, so now uh, you can see here, for a causal sequence the power of z would be negative, right? And for a non-causal sequence the power of z are positive. However, the data points are negative, x minus 4, minus 3, minus 2, like this. Here the data points would be positive. So it means that when the ROC is z greater than some value a, so this is a right sided causal. And if ROC is z less than some value a, then it is the left sided, or z less than a or minus a, for example, left sided non causal, right? So this is what we have to take care of while applying long division method to get the inverse z transform of the given um, z transform, right? So now, okay, so for a causal sequence, when we divide the numerator and denominator, so we get this type of representation, right? Because it is the right sided. So for a causal right sided, we have the inverse negative powers of z, and the data points are positive. However, for a non causal, we have the data points negative, and the power of z are positive, right? Then we have the partial fraction expansion method, right? In this method, we may have the xz or the z transform of any sequence like this, z plus 1 divided by z square plus 4z plus 4, right? So like this. So in this case, what we do is, or we may have xz like this, 1 by z square plus 4z plus 4. So in this case, what we do, we use the uh, partial fraction method. Basically, we factorize the denominator part of the given z transform. For example, in this one, what we will have z plus 1, in this one, sorry, we will have 1 upon z plus 2 square, right? So we can also write it 1 upon z plus 2 into z plus 2. So what we have done, we have factorized this thing. So we use partial fraction method, and then by using the partial fraction method, we try to find out the inverse z transform of the given z transform of a given sequence, right? Now in this, we again have to take care of the region of convergence. This is very important. Now if the region of convergence is greater than some value pk, so p is the some kth value, let us say it is some kth value of the given sequence, right? So it would give us a causal response. Okay, it is a right sided response. So this is what we have to take care of. So in that case, if we have this type of expression, so its inverse that transform or the solution would be this one. Similarly, if we have a non-causal response, that is, if ROC lies for the values of Z less than the kth value of the sequence, right? So in that case, our solution for the given Z transform would be this one, right? So in this, we have to write the solution. So ROC has to be taken care of in this case, because ROC has a significance, ROC as an importance in Z transform. ROC not only that uh, tells us the values for which the given Z transform will converge, but also it signifies, or it is related to the stability of the discrete time sequence, right? So that is why we have to take care of the region of convergence, right? Now let us take one example here. In this example, we have to find out the inverse Z transform of the following Z transforms, right? So the first Z transform is 1 upon 1 minus AZ inverse. So here the ROC should be greater than some value A, right? That is, this particular Z transform will converge for the values of Z greater than A. So that means this is a right-sided sequence, right? And it is a causal sequence. And the same Z transform we will take, but here the region of convergence will be less than the value of A. So this is some left sided sequence, and this is non-causal, right? So causal and non-causal, right? So let us take, now what is done here, we are using the long division method here in this case. So in a long division method, what we have done, we have taken numerator here and we are dividing it 1 minus a z inverse, right? Now as we know that for a right sided causal sequence, the power of z would be negative, right? This is what we have to take care of. And the values of x would be 0, x1, these are the positive values. Okay, so the data points are positive, however the power of z would be negative. This is what we have to take care of in case the ROC is for some values of z greater than a. Okay, right? So that means if we have a right-sided causal sequence, so in that case, the power of z would be negative and the data points are positive, right? So let us divide this one. So on dividing, so first we will take 1. So 1 into 1 is 1. 1 into minus, this is minus a z inverse, right? So let us subtract this one, simplify this one. So we have a z inverse now. Now if we multiply this sequence with a z inverse, so let us multiply a z inverse. So we are dividing this, basically we are using a long division method. Okay, now a z inverse would be here a z inverse, then it is minus a square z minus 2. So minus plus, so here it is cancelled. Then we have a square z minus 2. Now then we will multiply this with a square z minus 2, right? So we have, if we multiply this with this one, so we have a square z minus 2 minus a cube z minus 3. So minus plus and this is cancelled out and we have a cube z minus 3 and so on, right? So now we will take this quotient here. So this is the xz of the given sequence, means while dividing these two we have got 1 plus a z inverse plus a square z minus 2 plus and so on, right, like this. Okay, so now as you can see here, this is what we have. Now this is the, now because the power of z are negative, you can see here the power of z are negative but the data points. So if you compare this with, let us compare this one with xz is equal to x0 z0 plus x1 z minus 1 plus x2 z minus 2 plus x3 z minus 3. So what if you compare these two? So let us compare. So we'll get x0 is 1, x1 is a, x2 is a square, x3 is a cube, like this. So the inverse z transform of xz will give us xn, so which is 1 a, a square, a cube and so on, like this. Now either you can stop here or you can write it like this, because what we are seeing here, we are seeing that the power of a is increasing, so we can write it a raised to the power n and we can multiply it with the un. Now why we have multiplied this with un? Because why un? Because un is 1 for n greater than equal to 0, right? So let n is 0, so this x0 will be a raised to the power 0 into 1. So it is 1, so x0 is 1. Then we will take x1. X1 is, for n is equal to 1, so a raised to the power 1 into 1, because un will remain 1 for any value of n greater than equal to 0, right? So we have a here. So you can see it is a here. So this is how we can find out the inverse z transform using long division method, right? So either we can stop at this point, this is also acceptable, no issue, or we can simplify this further. This is totally up to us, no issue. Okay, so what we have understood here, for the region of convergence, so this particular z transform, this one will converge for all the values of z which are greater than some value a. So a could be any random value. So here a actually is representing the radius of the circle in the z plane, right? So if a is equal to 1, so we will say it is a unit circle. Okay, otherwise a can be greater than 1, less than 1, that is a different thing. Now Now let us come to the second. In the second part, we have been asked to find out the inverse Z transform of the same sequence, but here this particular Z transform will converge for the values of Z which are less than A. So that means this is a left-sided non-causal. So in left-sided non-causal, we have the xz where we have x0 or z x minus 1, sorry, z minus 1, then x minus 2, z2, yeah, minus 2, right? Then x minus 3, z minus 3, and so on. So it would be x minus 1, z 1 plus x minus 2, z2 plus x minus 3, z3, and like this. So you can see here the data points are negative, but the power of z is positive, right? So now when we have to find out the inverse z transform of a given z transform in which the region of convergence is all the values of z less than some value a. So as I said, a can be the radius of circle, right? So this could be a circle. So that means this particular z transform will converge for all the values of z which are lying in this particular circle, because the radius of this circle is a, right? Now, Now, as we have seen, what is done here, instead of like in the last, the same question, we have divided 1 by 1 minus a z inverse. However, here we have divided 1 by minus a z inverse plus 1, right? Just to get the negative data points and positive values of z. Positive values of the power of z, right? So on solving this one, you can see positive powers of z. So we have got this one, right? So if you compare this with uh, if you compare this with xz is equal to x minus 1 z1 plus x minus 2 z2 plus x minus 3 z3 plus x minus 4z4, and so on. So what you will get if you compare these two? So you'll get x minus 1 is uh, x minus 1 is minus a inverse, x minus 2 is minus a minus 2, right? So in this way we have got the, we can compare and we'll get the values, right? Now this is the sequence that we have obtained here. You can see we have taken all the data points. So these are the data points actually. These are the data points. So we have taken these data points here, right? And this would be the zeroth, or sorry, first data point basically, which is at minus 1. So this is at n is equal to minus 1. This is at n is equal to minus 2. This is at n is equal to minus 3. And this is at n is equal to minus 4, right? So now what we have done, we know that the power of a is changing. So we have written is minus a raised to the power n u minus n minus 1. Now why we have taken minus and minus 1? Because a causal sequence is because a non-causal sequence is actually having a negative shift. Okay, so that means a non-causal sequence. So if we take n here, so we have some positive values, we have some negative values, right? So this is plus 1, plus 2, plus 3 like this. It is minus 1, minus 2, minus 3 and it is 0. So a causal sequence will exist for these values. However, the anti-causal sequence will start from minus 1 here, right? So that is why we take u minus and minus 1. So this u minus and minus 1 is equal to 1 for all values of n less than 0. Okay, so for all values of n less than 0, it is 1. So we have taken it like this, right? So this is how we find out. So the in these two numericals, I hope you have understood clearly that it is simply division, nothing else. It is simple division. The only thing we need to take care of is the ROC, region of convergence. If ROC, that is the given Z transform, is converging for all the values of Z greater than some value A, so we will have uh, a right-sided causal sequence. If the region of convergence is for all the values of Z less than A, then we will have a left-sided non-causal sequence, right? Similarly, here in this numerical also, as you can see, we have to find out the Z inverse Z transform of this particular uh, Z transform. So we will use partial fraction here. So we'll use partial fraction here. We will use partial fraction here. So, uh, but here two conditions are given, that first is the ROC should be less than minus 2, and then ROC should be greater than 3, right? That means in this case, the given Z transform, this Z transform will converge for all the values of Z which are less than minus 2. That is, if you use, this is minus 1, let us say this is minus 2, so less than minus 2. So and here that means it may converge for this particular part, right? Now in this case, the given Z transform will be 1 and 2 and 3, for example this one. So it is like this. So given Z transform will converge for all the values of greater than 3, like this. Okay, so now in the first question, the region of convergence is less than minus 2. So we'll have this. Now, when we open up this bracket, this one, so z square minus z minus 6, if we factorize this one, so we have z plus 2 and z minus 3, right? So these are the factors, right? So we have factorized this one, then we'll have the partial fraction. So the partial fraction is basically used like this: z plus 2 z minus 3 is equal to a by z plus 2 plus b by z minus 3, right? A by z plus 2 plus b by z minus 3. So we will solve this one. So we have a z minus 3a plus b z plus 2b divided by z plus 2 by z minus 3. So this is cancelled out here. So we have a plus bz is equal to z. We'll compare, we'll equate the relevant terms, right? Then we have minus 3a plus 2b is equal to 0, right? So we have a plus b is equal to 1, and we have b is equal to 3a by 2. So on solving this one, we'll get a is equal to uh, plus 1 by 5 and b is equal to minus 1 by 5, right? So this is how we'll get the answer. Okay, so now uh, this can be written as 1 by 5 1 upon 1 minus 3z inverse. We can write it like this: minus 1 by 5 1 upon 1 plus 2z inverse, right? Or we can also write it like this: 1 by 5 1 upon 1 minus 3z inverse minus 1 by 5 1 upon 1 minus minus 2z inverse. right? Like this also we can write it. Okay, so when we apply the inverse z transform, so we will take care of this formula, this one, because so the answer would be kth value raised to the power n into un, right? So here what will be the answer? 1 by 5. So this is kth value minus 3 raised to the power n into u. Now, the region of convergence is less than minus 2. That means it is a non-causal. So, we will have u n minus n minus 1. Minus n indicates the negative values of the samples, and minus 1 we have taken because it is negatively shifted, right? Then we have minus 1 by 5 into. So, we have this minus uh, 2 raised to the power n, and then we have u minus n minus 1, right? So on solving we'll get this answer here. Now if the region of convergence is greater than 3, so in that case we will have a different approach, right? A different approach means we will have the positive data points here, as we have taken the negative data point, na? This is negative data points. So for this we have positive data points. You can see here these will also be positive for all the values of n greater than equal to 0, and this would be 1 here. So this is how we find out the uh, inverse z transform of the given sequences by using the uh, uh, long division method and partial fraction method. So I hope you have understood this concept. You can uh, solve many more numerical problems related to these topics. And this is all about today's lecture. Thank you so much.